Okay. So the process of getting a line of position off of a celestial observation is going to take multiple playlists for me to actually like explain in detail. So the way we're going to go forward with the preceding few videos, not few, a lot of videos, is going to be I've set up 3 different problems on these 3 pages, and we're just going to very slowly go through each of them. Now, all of these are just a single observation of the sun. Here you can see it's the 18th of August at 10:36. We take a sight of the lower limb of the sun. Next, we have 4th of June at, where does it say? 9:15, we take a shot of the sun. And then over here, we've got 21st of November. This is just going to be done so you can see all the variety of different things that could impact and change the way a sun sight would work. So like some of them happen in the summertime, some of them happen in the winter, some are in the eastern hemisphere, some are in the western hemisphere, and then some are in the north and some are in the south. All of that is going to impact and have an influence over how these work. You'll see that as we go forward. So I wanted to pick at least 3 to cover all our bases there. Now, frustratingly, before we can do anything here, anything that has anything to do with CellNav, you'll see with most of these problems, how it's usually set up is you're given a position sometime earlier in the day. In this case, we've got at 6 in the morning. And then your shot happens later on. The same is true for all the others. Here's 6:30, and then the shot happens at 9. Here's 4:30, and the shot... Oh, okay. The shot actually happens at the time of... at the time listed here for this one. That's helpful. But what this means is that this position is not representative of the time at which you actually measured the sun. So in basically every CellNav problem, you're going to have, the first thing you're going to have to do is actually to take the plotting sheets and set up your problem on the sheet to get a DR position that's relative to when you're actually going to be measuring. And then once you do that, you can move on from there. This is frustrating because I know a lot of people, they just want to get straight to work. Like they see the written problem, so they want to just write out the math on the piece of paper and they don't want to deal with the plotting until the very end. You can't do that. You have to start with plotting, like the very basics, just set up the sheet and set a course along it. And then once you get the DR position, then you can come back and do the math and then go back to the plotting sheet to actually get your LOP from there. So that's how we're gonna do this. I also wanna make one note. None of these problems are gonna give us a fix because each of them are only a single shot. A single shot will give you 1 LOP, but that doesn't tell you anything. The reason I chose 3 different ones though is, like I said, so we can show all the different factors that go into getting a line of position based on what time of year, when, where on the earth you are. As a result, this is not going to end with like anything productive. We're not going to have a fix at the end, but it's later on I'll do a problem where we actually take a running fix across a single day to find our exact position to show you that. These videos will just be based on getting LOPs. So we're going to start with the first one, and let's just read out the entire problem. I hope you can read my handwriting. So it's the 18th of August, and at the 18th of August, you had a 0600 dead reckoning position of 19 degrees 48 minutes north and 108 degrees 34 minutes west. You were on course 166 true at 16 knots, and at 10:36 in the morning, you took an observation of the sun's lower limb. So, you know, you brought the bottom of the sun to the horizon, not the top of the sun. The sun's lower limb had a height of 65 degrees, 6.3 minutes. The exact chronometer time, which we'll get to later, was 05:34:48 with a chronometer error of 1 minute 24 seconds slow. Your height of eye was 61 feet. Your index error was 0.6 minutes off the arc. Okay, what do we need to start just to set this up? Well, we need our DR position, and we need to set our track line so that we can end with a DR position relevant to the time that we took our shot. So, at 0600, we were at 19 degrees, 48 minutes north, 108, 34 minutes west. We're headed 166, which is about just about southeast. So, I'm gonna zoom out here. Because we're headed southeast, like probably southeast, it's pretty much this track, generally like this right here. What that's gonna mean is we're probably gonna want our first DR position somewhere up here so that we can then move along the track further down so that when we actually have the DR that we're working off of to plot our LOP, it's in the center of the page, which just makes it easier to work with. So let's see. In that case, if our first position is at 19 degrees, 48 minutes north, I would say it would be smart to set this at 19 degrees because then 1948 would be somewhere up here and we'd be moving down from there. So that's what we're gonna do. 19 degrees north. By the way, before you even start, you should probably put some identifying information at the top of the chart. So I'm just gonna put, what is it, the 18th of August? 18th of August. Just so you can remember what you're working with from there. So here we've got 19 north, 20 degrees north, 21 degrees north, 18 degrees north, 17 degrees north. Now, from here, we're gonna actually set our longitude lines. We don't really need to worry about what meridians are what just yet. So if we've got 19 as our central parallel, we'll come up to the 19 line here, and the 19 line here. We'll come over to this side, and we'll do the same. Then we'll get our triangles. We'll set 1. Line it up perfectly. We can draw a parallel there, or a meridian there. And a meridian right there. Okay. I'll do it just for the practice, for the sake of practice, but seeing as we're only working with one LOP here, we're probably not going to need more meridians off to the side. However, if you were doing a day's work, you would probably need to set as many meridians as you could to just fill out the entire page. So we're just going to demonstrate that here, meaning you make a little mark, 60 degrees of longitude to either side of the 2 meridians you've already set. And then once that mark is in place, I lost my pencil. Here it is. Now you can set a perpendicular line to them. And one to this one. Okay, now I've got the whole page measured out. We should set our meridians. Let's see, we said we were at 108:43 minutes west. So I would say it would be smart to set this first one as 108 degrees, because that would set us somewhere around here, so then we move towards the center of the page. Again, you want the majority of your work to be happening in the center of the page because that just makes things easier. So we'll do 108 degrees west up here. Let me zoom in. Remember, west goes this way, so we've got 109 degrees here, 110. Then back here we've got 107. And 106. Now the last thing we need to do for the matter of setting things up is we've got to set our longitude scale. So we take 60 minutes of longitude, then we come down to our scale over here, and we bring it down, and it should land just under the 20 because we're working with 19 here. So where else would it go? So then you bring your triangle down, set it perpendicular to the meridian. Once that's in position, come across 19 degrees north. Perfect, and that's what we'll use for all of our measurements of longitude. Now we actually set our starting position. So let's see. Our starting dead reckoning position was 19 degrees, 48 minutes north, 108 degrees, 34 minutes west. So first, let's just mark the latitude. Let's see. 19 degrees. Here we've got 30, 40. There's 48 right there. So we're going to just draw a faint line out from there, just so it can be easily erased later. And then our longitude was 34 minutes west of 108. So we come down to our longitude scale. We set one side of our divider at 30. Then we've got to bring this to 8, which, there you go, that's 8 right there. Then we bring that to the little horizontal line we drew. Hold it in position where it landed. Mark that point. And there. That is our 0600 DR position. And we can erase the rest. Once again, I should grab my eraser. It's somewhere, I just don't know where it is. You should use a large eraser, not your pencil eraser, but whatever. Now that we've got our position, we got to mark our course. So our course is 166 degrees true. So we take our triangle, measure out, there's 166 right there. So you can see. Then, this is gonna get tricky because I've got the camera stand right there. We have to shift this over. So that it lands right on 600. Draw a track line. And you generally want to have the track line go all the way to the end of the page, the sheet, like so. Just for the sake of, you know, it's easier for you to draw it too short and have to extend it than it is for you to draw it too long, so there's no harm in drawing it too long. Now you got to mark and label the track up here. So we've got course 166 degrees true. That way. At a speed of 16 knots. Speed 16 knots. Now the whole point of all of this is to set our next DR position. So the problem shows us having we take the shot at 1036. So the first thing we got to do is we've got to find how far away 1036 is from 0600. Well, it's 4 hours and 36 minutes, correct? Like, that's easy. So we have to do a 60 D Street problem to find how far away we're going to be in 4 hours and 36 minutes. So we don't even need to write that out because I think it's good practice to not have to. 4 hours is just 4 sets of 60, so we do 4 times 60 plus 36 minutes. So minutes, 4 hours, or 276 minutes times 16 knots divided by 60. We're going to go 73.6 miles. So then what we do, let me zoom in here. 73. So here's 60 because it's a degree. Here's 70. And then 1, 2, 3. And then 6 is just a little bit above 3. There. You measure that along your track line. Make a little tick mark where it ends. And then label that 1036. Yes, correct. Now what we need to do is we need to actually measure where that is so that we know the latitude and longitude of our DR at the time of our site. So firstly, just line your triangle up with a meridian. Draw a quick little line across. Nice and faint, just so we see where it lands. And it lands at the 37, down at the level of 18 degrees. So we know that our latitude, we're gonna write it out the problem here, 1036 DR is 18 degrees, 37 minutes north. And now we have to measure our longitude. So now that we've got that little horizontal line already drawn, measure the length of it and bring it down to the longitude scale. It looks like it's about as long as wow, it's actually, I wasn't expecting that. It's actually perfectly 20. Okay, so it's exactly 20 minutes, meaning our longitude is 108 degrees, 20 minutes west. So that's how you get, let's zoom, there we go. That's how you get our DR position for the time that we actually take the measurement of the sun for this problem. I was not expecting that to take 18 minutes. Obviously, I was talking through everything. So I don't find it necessary to set this up on camera for every single one of them. So I'm going to do the next two off camera to save you the monotony of it. And then from there, we'll actually start doing the problems.